You're holding a coin in your hand. You toss it into the air, watch it spin under the light, then it falls back down. Heads or tails? You're sure it was decided the moment it left your fingers, right? You just didn't know the answer yet. But there is a strange world where that coin doesn't choose heads or tails until the exact moment you look at it. Even more mind-bending than that, while it's floating through the air, unseen by anyone, it is both heads and tails at the same time. Not, maybe one or the other, but truly both at once. Sounds confusing? Good. Because that's the world we're about to step into tonight. Now, think about these 3 questions. First, that moon hanging quietly in the night sky, does it really exist when you're not looking up at it, or does it only appear when someone observes it? Second, a tiny speck of dust, smaller than anything you can see dancing in a beam of sunlight, could it exist in 2 different places at the same time? And finally, the reality we live in, does it depend on whether our eyes are open or closed? These questions sound absurd. They go against everything you've been taught since childhood. And yet, they are exactly what science has uncovered over the past 100 years. Tonight, we're going to explore the strangest world humanity has ever discovered, a world where nearly everything you think you know about reality might be completely wrong. This world isn't on Mars. It isn't hidden inside a science fiction novel. It's right here, inside every atom that makes up your hand, inside every ray of light that reaches your eyes. This isn't imagination. This is real science, proven by thousands of experiments. Welcome to SleepLore, where we explore the deepest ideas of the universe in the gentlest, sleepiest way possible. Whether you're lying in bed, curled up on the sofa, or riding a train home, find a position that feels truly comfortable. Because tonight's journey may completely change the way you see the world around you. Let's turn the clock back more than 120 years, to the dawn of the 20th century. At that time, scientists were living in a golden age of confidence. They believed they had almost completely figured out the universe. Newton, with his famous laws of motion, had explained why apples fall to the ground and why planets orbit the sun. Maxwell, a brilliant Scottish physicist, had written down elegant equations that explained light, electricity, and magnetism. Everything seemed to fit together like perfectly cut puzzle pieces. Thermodynamics, mechanics, electromagnetism, all neatly organized inside thick, authoritative textbooks. Some of the most respected scientists of the era even declared that physics was essentially finished. They said only a few minor details remained to be cleaned up, like bits of dust left in the corners after a thorough sweep. A few even advised young students not to study physics at all, because all the big questions had already been answered. They were wrong. Spectacularly wrong. Because hidden inside those small dark corners, inside those supposedly insignificant details, were secrets powerful enough to completely overturn our understanding of reality. All it took was one small problem involving light and heat to bring down an entire castle of knowledge built over centuries. The trouble began with something incredibly simple. When you heat an object, it glows. You see this everywhere. A metal rod placed in a forge turns from black to deep red, then orange, then yellow, and finally blinding white as the temperature rises. A burning candle gives off a warm yellow light. The filament inside the light bulb in your home works the same way. Electric current heats the metal until it shines. This phenomenon is so common that no one ever questioned it. But when scientists tried to explain exactly why it happens, they ran into a terrifying problem. According to the classical equations they trusted, as an object gets hotter, it should emit more and more energy at shorter wavelengths. That sounds reasonable, until you follow the math all the way through. The equation said that at very short wavelengths, like ultraviolet light, the emitted energy should increase without limit. Without limit. Think about what that means. It means a tiny piece of coal, once heated, should release more energy than the entire universe combined. Your household heater would become an infinite energy source. Everything would glow violently, blasting out unimaginable levels of deadly radiation. Of course, none of this happens. Your heater does not destroy the universe. A piece of coal gives off a modest, cozy glow, nothing unusual at all. But the mathematics, the same mathematics scientists had trusted for hundreds of years, insisted otherwise. Physicists tried everything. They tweaked one equation, adjusted another. They checked every step of their calculations. No matter what they did, that horrifying infinity kept coming back, like a curse that refused to be broken. The problem even earned a dramatic name, the ultraviolet catastrophe, because it appeared in the ultraviolet part of the light spectrum. For years, no one knew what to do with it. Then, in 1900, a German physicist named Max Planck entered the story. Planck was not a revolutionary by nature. He was careful, conservative, deeply committed to classical principles. He had no desire to tear physics apart. He just wanted to fix that one annoying equation. Planck spent months wrestling with the numbers, trying every approach he could think of. Finally, in a moment of desperation, he decided to try an idea that felt completely insane. What if energy could not be emitted in any arbitrary amount? What if energy had to come in small, discrete packets, like coins? Think about it. You cannot have half a coin or 1/3 of a coin. You can only have one coin, 2 coins, 3 coins, whole numbers. Planck suggested that energy works the same way. It does not flow smoothly like water. Instead, it jumps in tiny steps, like climbing a staircase, one step at a time, never stopping in between. He called these smallest packets of energy quanta. He even calculated their size using an incredibly tiny number we now call Planck's constant. When Planck put this idea into his equations, something miraculous happened. The terrifying infinity vanished. The equations suddenly produced sensible results. Even better, they matched experimental measurements perfectly. The problem was solved. The ultraviolet catastrophe had been avoided. But Planck was not happy with his own solution. He thought of it as nothing more than a mathematical trick, a clever hack to make the numbers behave. He did not believe energy truly came in discrete packets. He was convinced someone would eventually find a better explanation, one that did not rely on such a strange assumption. He was wrong. Without realizing it, Planck had opened a door to an entirely new world, a world where everything we thought was obvious would be questioned. While Planck was uneasy about his energy packets, another mystery was waiting in the shadows. This one involved light, metal, and tiny particles called electrons. It had long been known that shining light onto a metal surface can sometimes knock electrons out of the metal. At first glance, this seems simple enough. Light carries energy, that energy is transferred to the electron, and if the electron gets enough energy, it escapes. Straightforward, right? But when scientists studied the effect more carefully, they found something deeply strange. According to the classical wave theory of light, making the light brighter, increasing its intensity, should give the electrons more energy, just like stronger ocean waves push a boat harder. But that is not what happens. No matter how blindingly bright the light is, the electrons fly out with the same energy. The only thing that matters is the color of the light, or more precisely, its frequency. With red light, no matter how intense, the electrons refuse to move. But with violet light, even a faint beam makes electrons pop out instantly. It is as if there is a locked door, you can have a million wrong keys, but a single correct key opens it immediately. This made no sense under wave theory. In that framework, brighter light means stronger waves, and stronger waves should have a stronger effect. Reality stubbornly disagreed. In 1905, a young man working at a patent office in Switzerland decided to tackle the problem. His name was Albert Einstein, and he was only 26 years old. Einstein had read Planck's work and thought deeply about those strange energy packets. Then he had a bold idea. What if light does not just carry energy in packets? What if light itself is made of those packets? In other words, what if light is not a continuous wave spread through space, but a stream of tiny energy bullets flying at the speed of light? Einstein called them light quanta, what we now call photons. Each photon carries a specific amount of energy, determined by its frequency. Violet photons carry high energy. Red photons carry low energy. When a photon hits an electron in a metal, it transfers all of its energy in a single instant. If the photon has enough energy, meaning the light has a high enough frequency, the electron escapes. If it does not, then no matter how many photons hit the metal, the electron stays trapped. Just like having millions of wrong keys will never open a lock. This perfectly explained why brightness does not matter, but color does. Brighter light simply means more photons. But if each photon is too weak, having more of them changes nothing. A million plastic hammers will not break a concrete wall, but one solid steel hammer will. Einstein's idea matched experiments flawlessly. It explained everything. But it also raised a question so profound that scientists would wrestle with it for decades. So what is light? A wave or a particle? For centuries, experiments had shown that light is a wave. It diffracts, it interferes, it behaves exactly like waves should. And yet Einstein was now saying it is made of particles, tiny bullets flying through space. Einstein's answer was stranger than either option. Light is both a wave and a particle. In some situations it behaves like a wave, in others like a particle. How it appears depends on how you look at it, how you measure it. This sounds like a contradiction. In our everyday world, something must be one thing or the other. A ball cannot be both a water wave and a stone. But in the quantum world, those rules no longer apply. Einstein's work on the photoelectric effect was so important that it earned him the Nobel Prize in 1921, not for his famous theory of relativity, but specifically for uncovering the quantum nature of light. The scientific world began to realize they were facing something entirely new, something deeply unfamiliar. If light could be both a wave and a particle, what about everything else? Was reality playing by rules we had never even imagined? To find out, we need to look at one of the strangest, simplest, and most profound experiments in the history of science. An experiment that uses nothing more than two tiny slits in a sheet of material, yet has the power to shake the foundations of reality itself. Now let's talk about an experiment, not the kind that requires expensive machines or cutting-edge laboratories. This one is so simple that almost anyone could do it, at least in theory. What do you need? A light source, something as basic as a flashlight. A thin card with two tiny, parallel slits cut into it. And a wall or a screen behind it to catch the light. That's it. Just three simple things, yet they're enough to produce one of the strangest and most profound discoveries in the history of science. Many famous physicists have called this the most dramatic experiment ever performed. Some have even joked that it deserves an Oscar nomination, because it has everything: mystery, suspense, completely unexpected results, and an ending that leaves you sitting in silence, wondering what life even means. But before we run the experiment, we need to understand what we expect to happen. In the classical world, waves and particles behave very differently. Let's look at two cases. First, waves. Imagine standing at the beach, watching waves roll toward a wall with two openings in it. The water waves pass through both holes, spread out on the other side, and then overlap. Where crest meets crest, the waves add together and grow taller. Where crest meets trough, they cancel each other out. The result is a striped pattern, regions of strong waves and weak waves alternating with each other. Scientists call this an interference pattern. Now the second case, particles. Instead of water waves, imagine throwing small marbles at a wall with two holes. Some marbles go through the left hole, some through the right. They don't interfere with each other. They don't form any special pattern. On the screen behind the wall, you just see two piles of marbles, each one lined up with a hole. Simple. Intuitive. Nothing strange. So what about light? Does it behave like a wave or like a particle? Scientists have been doing this experiment for a very long time, going back hundreds of years. When they shine light through two slits, the result is unmistakable. An interference pattern appears. On the screen, instead of two simple bright bands, they see many alternating bright and dark stripes, exactly like what waves produce. This seems to settle it. Light is a wave. People have known this since the 19th century. Maxwell's equations explain it beautifully. Everything seems neat and tidy. Until Einstein shows up with the idea of photons, tiny packets of light, like little bullets. Suddenly an uncomfortable question appears. If light is really made of discrete particles called photons, why does it create a wave-like interference pattern? To answer that question, scientists decided to do something bold. They turned the light source way down. Really way down. Down to the point where only a single photon is emitted at a time. One lone photon travels toward the two slits, then hits the screen behind them, leaving a tiny dot of light. Now pause for a moment and think about this. We have just one photon. It can't interfere with another photon, because there is no other photon. It has to go through one slit or the other, left or right. By ordinary logic, if we fire enough photons, we should end up with two clusters of dots behind the two slits, just like the marbles. But that's not what happens. At first, when only a few photons hit the screen, everything looks random. A dot here, a dot there, no obvious pattern. But the scientists are patient. They let the experiment run, 1 hour, 2 hours. Thousands of photons, tens of thousands of photons, one by one, passing through the slits and striking the screen. Slowly, a pattern begins to emerge. The dots are not evenly distributed. They gather into stripes. Bright stripe, dark gap, bright stripe, dark gap, exactly like an interference pattern. How can that be? Each photon travels alone. It has nothing to interfere with. So what is it interfering with? The only answer that seems to make sense, even though it sounds insane, is this. Each photon is interfering with itself. Somehow, a single photon appears to pass through both slits at the same time, like a ghost splitting in two, taking both paths, then meeting itself on the other side and creating interference. That's already hard to believe, but the strangest part is still ahead. Scientists decided to settle the mystery once and for all. They placed extremely small, extremely sensitive detectors right at the slits. The goal was simple, to see which slit the photon actually goes through. Left or right? Or truly both? These detectors don't do much. They just observe. They record information. That's it. They don't push or pull or physically disturb the photon in any meaningful way. They turn the detectors on and run the experiment again, firing one photon at a time, just like before. The interference pattern disappears. Completely. Cleanly. As if it never existed. Instead, the screen shows only two simple bright bands directly behind the slits, exactly what you would expect from ordinary particles. The photons now behave like tiny marbles. Half go through the left slit, half through the right. No interference. No wave behavior. No magic. The scientists turn the detectors off and run the experiment again. The interference pattern comes back, beautiful as ever. Detectors on, pattern gone. Detectors off, pattern returns. On, gone. Off, back again. They repeat this over and over. The result is always the same. When no one is looking, photons behave like waves, spreading out and creating a stunning interference pattern. When a measuring device is watching, even one that barely interacts with the photon at all, the photon immediately chooses to behave like an ordinary particle. This is not how things work in our everyday world. If you're not looking at a parked car on the street, the car is still there, in the same spot. Your act of looking doesn't change its position. But at the quantum level, things are different. The behavior of a photon, whether it acts like a wave or a particle, seems to depend on whether it is being observed. Not because the measuring device physically disturbs it. Scientists have designed detectors that interact as little as possible. The result is still the same. The problem isn't how we observe. The problem is whether observation happens at all. At the deepest level, the universe seems to care about whether someone is watching. Some scientists describe it like this. When unobserved, a photon exists in a fuzzy state, a cloud of possibilities, something spread across many paths at once. It doesn't have a single location or a single route. It is all possibilities at the same time. Only when we measure, when we look, does that cloud of possibilities collapse into one specific point, one specific path, one specific reality. As if the universe itself remains undecided until someone asks a precise question, and only then is it forced to give a definite answer. This experiment has been repeated thousands of times, in hundreds of laboratories, by countless scientists. They've done it with photons, with electrons, even with large molecules made of hundreds of atoms. The result is always the same. When unobserved, wave behavior, interference, spreading across many paths. When observed, particle behavior, a single path, no interference. This is not a flaw in the equipment. It's not human error. This is how reality behaves at the quantum level. Some people find this terrifying. It suggests that reality is not as solid as we think. It isn't fully determined. It doesn't exist independently of observation. In some sense, our act of observing helps bring reality into being. Others find it beautiful. It suggests that the universe is more flexible, more open, more full of possibility than we ever imagined. It isn't a rigid clockwork machine following fixed rules. It's something more alive, more responsive, more strange. The double-slit experiment doesn't give us easy answers. Instead, it forces deeper questions. What does it mean to observe? When is reality decided? Is everything just possibility until we look? What role do humans play in this universe? These aren't empty philosophical puzzles. They arise from real experiments, carefully measured, endlessly repeated. This is science, but science pushed to the edge of understanding, where physics meets philosophy, where the question of what is collides with the question of why. The double-slit experiment tells us one thing for sure. The universe is not a simple clockwork machine. It is a tapestry woven from possibilities, something shimmering and shifting, something that responds to our gaze in ways we still don't fully understand. Photons wink at us when we're not looking, then freeze when we turn back. The universe is playing a game with us, a strange, mysterious, and deeply captivating game. So what is really going on here? How do we describe a world where everything is possibility until it is observed? How can mathematics capture what might be instead of what is certain? To answer those questions, we need a new tool. A new equation. A new way of thinking about reality. A way of seeing that doesn't just describe what things are, but what they could become. And that's when an Austrian physicist named Erwin Schrödinger enters the story, carrying an equation that would change everything. In 1926, an Austrian physicist named Erwin Schrödinger sat alone in a small room in the Alps, wrestling with the strange questions the quantum world was beginning to ask. He knew electrons did not behave like tiny billiard balls. They formed interference patterns like waves. They showed up in places no one expected. They seemed to spread through space in ways classical physics simply could not explain. He needed an equation. An equation that would describe not where an electron is, but where an electron could be. Not certainty, but possibility. Not a point, but a cloud. After weeks of relentless work, Schrödinger wrote down an equation that was beautiful and elegant. It was not long. It was not flashy or complicated in appearance. But what it described was utterly revolutionary. You do not need to understand the math to grasp the core idea. In fact, Schrödinger himself was not entirely sure what the deeper philosophical meaning of his equation really was. But it worked. It predicted exactly what experiments measured. And that was what mattered most. At the heart of the Schrödinger equation is a concept called the wave function. Scientists usually represent it with a Greek letter pronounced psi, which looks a bit like a tiny three-pronged fork. The wave function is not something you can see or touch. It is not a real wave on water or in the air. It is a mathematical tool, a way of describing everything we can know about a quantum system. To understand it, imagine this. You are standing in a dark room, blindfolded. Somewhere in the room, there is a cat. You have no idea where it is. You throw a small ball and listen carefully for the sound when it hits something. Then you throw another ball. One by one, you slowly build a mental map of where the cat might be. Some areas feel more likely, the cat is probably here. Other areas feel less likely, probably not there. You do not know for sure, but you have a picture of probabilities. That is exactly what the wave function is. It does not tell you where the electron is. It tells you this is where the electron is likely to be, this is where it is less likely to be, and this is where it is almost impossible to be. It is a probability map of all the places a particle could appear. The amazing thing about the Schrödinger equation is that it lets us calculate how this wave function changes over time. Just as you can predict how waves on water will move, the Schrödinger equation lets us predict how a particle's probability wave will spread out, contract, and oscillate. But something very strange happens when we measure. As long as the wave function is left alone, gently evolving and spreading through space like fog, everything is smooth, continuous, and predictable. The electron exists as a cloud of possibilities, a little bit here, a little bit there, everywhere at once in different proportions. Then you measure. You place a detector. You look. Instantly, not gradually but all at once, the entire cloud of probability collapses into a single point. The wave function collapses. The electron suddenly is in one specific place, no longer everywhere at once. It is like lightning in the night, a sudden flash that reveals one hill while everything else remains hidden in the fog. Before the measurement, the electron could be at A, could be at B, could be at C, all at the same time to different degrees. After the measurement, the electron is at B definitively. Clearly. All other possibilities vanish. This is nothing like classical physics. In the everyday world, when you do not know where something is, it simply means you lack information. The car is still in one specific place, you just have not learned where it is yet. When you look, you do not change the car's position. You only gain knowledge. But in the quantum world, before measurement, the electron truly does not have a definite position. It is not somewhere we just have not discovered yet. It really is a cloud of possibilities. The act of measurement does not just reveal an outcome. It creates one. The Schrödinger equation is not just a beautiful theory. It explains things classical physics never could. Take the hydrogen atom, the simplest atom in the universe, made of just one proton and one electron. For decades, scientists could not understand why the electron did not fall into the proton. According to classical physics, the electron orbits the nucleus like a planet orbits the sun. But a moving electric charge must radiate energy, lose that energy, and eventually spiral inward. Every atom should collapse almost instantly. But that does not happen. Atoms are stable. Why? When Schrödinger applied his equation to the hydrogen atom, something stunning appeared. The electron is not a tiny particle orbiting the nucleus. Instead, it is a standing wave, a stable vibration pattern surrounding the nucleus, much like sound resonating inside a bell. These patterns create regions where the electron can appear, not sharp orbits like planets, but probability clouds. Scientists call them orbitals. You have probably seen pictures of them in textbooks, strange shapes like stretched spheres, dumbbells, or flower petals. Those shapes are not just illustrations. They represent where the electron is most likely to be found when you look. The electron is not at a single point. It spreads across the entire region like a cloud. The Schrödinger equation also predicts the exact energy levels of these probability regions, explaining why atoms emit light at specific colors, and why chemical reactions happen the way they do and not some other way. It even predicts a phenomenon that sounds completely insane, called quantum tunneling, where a particle can appear on the other side of a barrier it should never be able to cross according to classical physics. It sounds absurd, but it has been observed countless times. The Schrödinger equation became the foundation of modern chemistry, materials science, and semiconductor technology. The computer you are using, the phone in your pocket, all of it works because of predictions made by this equation. It is one of the greatest achievements of the human mind, an equation that captures vagueness, possibility, uncertainty, things once thought impossible to put into mathematics. But the Schrödinger equation also reveals something unsettling. It shows that there are fundamental limits to what we can know. 1 year after Schrödinger published his equation, in 1927, a young German physicist named Werner Heisenberg discovered something shocking. He realized there is an absolute limit, built into the structure of the universe itself, on how precisely we can know things. Specifically, Heisenberg found that you cannot know both the exact position and the exact velocity of a particle at the same time. Not because your instruments are bad. Not because you are clumsy. But because the universe does not allow it. This principle has a simple mathematical form with profound consequences. It says that the uncertainty in position multiplied by the uncertainty in momentum must always be greater than or equal to a tiny number. What does that mean? It means if you know exactly where a particle is, you cannot know how fast it is moving. And if you know exactly how fast it is moving, you cannot know where it is. The clearer one becomes, the fuzzier the other must be. This is a cosmic trade-off, a balance built into reality itself. A helpful way to picture this is to imagine trying to hold fog in your hands. If you open your hands wide, the fog spreads out. You have more fog, but no idea exactly where it is. If you squeeze your hands tight, trying to pin it down, the fog slips through your fingers and disappears. The harder you try to hold it, the more you lose. That is exactly how the universe behaves at the quantum level. You cannot grab an electron and say, here it is, exactly here, moving at exactly this speed. The universe does not permit that kind of certainty. The uncertainty principle is not just a mathematical curiosity. It has enormous real-world consequences. In fact, it explains why you exist. Let us return to the old question, why does the electron not fall into the nucleus? In an atom, the negatively charged electron is strongly attracted to the positively charged nucleus. Like an apple falling toward Earth, the electron should fall straight in. But the uncertainty principle prevents this. If the electron fell into the nucleus, it would be confined to an incredibly tiny space, its position would be known with extreme precision. According to the uncertainty principle, that would make the uncertainty in its velocity enormous. The electron would have to be capable of moving at every possible speed, from zero up to nearly the speed of light. That would require an immense amount of energy, in fact an infinite amount. The universe says no. Energy cannot be infinite. So the electron cannot fall into the nucleus. Instead, it must hover at a certain distance, in the probability regions we call orbitals. The uncertainty principle creates a kind of quantum pressure, or resistance to confinement. It prevents electrons from being squeezed too tightly. It keeps atoms stable. It is the reason matter does not collapse into an infinitely dense lump. Without the uncertainty principle, you could not exist. No stable atoms, no molecules, no chemistry, no life. This uncertainty, which at first sounds like an annoying limitation, turns out to be one of the most essential features of the universe. Many people feel disappointed when they first hear about the uncertainty principle. They think, so you are saying we cannot know things exactly? It sounds like failure, like a limit of human ability. But that is not what Heisenberg discovered. He was not saying our instruments are not good enough. He was saying no instrument, no matter how perfect, could ever overcome this limit. Because the limit is not in our tools. It is in reality itself. Particles do not have exact positions and exact velocities at the same time. Not because we do not know them, but because they do not have them. The idea of a particle being exactly here and moving at exactly this speed simply does not exist in the quantum world. Some philosophers even find this liberating. It means the universe is not a rigid clockwork machine where everything is predetermined. There is flexibility, openness, room for novelty. The uncertainty principle allows wonders like quantum tunneling, like stable atoms, like the entire richness of chemistry. Without it, the universe would be rigid, dull, frozen. So perhaps instead of being sad that we cannot know everything exactly, we should be amazed that the universe leaves a little room for surprise, for possibility, for the beauty of uncertainty. Now we have the Schrödinger equation, describing the world as clouds of possibility, and the uncertainty principle, telling us that perfect certainty is impossible. All of this leads to an even bigger, stranger question. If particles are not in one specific place, and do not have one specific velocity, then where are they? What are they doing? The answer is even crazier than anything we have seen so far. They are everywhere at once. They are doing everything at once. Until we look. Let's go back to the coin we talked about at the beginning of the video. In the everyday world, when you toss a coin into the air, it always lands one of two ways, heads or tails. You might not know which one it will be, but you are sure of one thing. From the moment the coin leaves your hand, the outcome is already decided. The physics of the spin, the angle, the force, all of it has already locked in the result. You just don't know it yet. That is a classical coin. Now imagine a quantum coin. This coin is tossed into the air, but instead of being already heads or already tails while it's flying, it exists in a strange state. It is both heads and tails at the same time. Not, maybe this or maybe that. Not, undecided. It is genuinely both. Only when the coin lands, when you look at it, when you observe it, then and only then does it choose a side. Before that moment, it truly is both heads and tails, blended together in a way our brains cannot really picture. Physicists call this quantum superposition. It is one of the core ideas, and one of the strangest, in the quantum world. At the smallest scales of the universe, things do not have to pick a single state. They can exist in multiple states at once, until something or someone forces them to choose. An electron can spin clockwise and counterclockwise at the same time. A photon can travel along path A and path B simultaneously. A particle can be at position X and position Y in the same instant. This is not poetry. It is not a metaphor. It is a measurable, tested reality, confirmed thousands of times in laboratories. In 1935, Erwin Schrödinger, the same man who wrote the wave equation, was sitting with these ideas and feeling deeply uneasy. Superposition made some sense for tiny particles. But did it really apply to larger objects? To show how absurd it would be to apply quantum rules to the everyday world, he came up with a thought experiment. It became so famous that almost everyone has heard of it, even if they never studied physics. Here is the experiment. You place a cat inside a sealed box. Next to the cat is a tiny radioactive atom, a detector, and a vial of poison. The setup is simple. If the atom decays, the detector notices, triggers a mechanism, breaks the vial, and the cat dies. If the atom does not decay, nothing happens and the cat lives. Now comes the quantum part. According to quantum mechanics, the radioactive atom exists in a superposition, both decayed and not decayed, until it is observed. That means the entire system, the detector, the poison vial, and the cat itself, must also be in a superposition. The cat is both alive and dead. Not alive or dead and we just don't know yet, but genuinely alive and dead at the same time, until someone opens the box and looks. Schrödinger did not propose this because he believed it was real. Quite the opposite. He wanted to show how ridiculous it would be if quantum rules really applied to large objects. He was saying, Look how crazy things get if we pretend the big world works like the quantum one. But the paradox took on a life of its own. It became a symbol of quantum physics, showing up on t-shirts, in movies, in comics. Schrödinger's cat is now shorthand for quantum uncertainty. The real question behind the thought experiment is this. Somewhere between a tiny atom and a full-sized cat, between the quantum world and the classical one, where is the line drawn? Why can an electron be in two places at once, but a cat cannot? There is still no fully satisfying answer. But here is the interesting part. Superposition is not just an abstract idea. It is already being used in real technology. The computers you use every day run on bits. Each bit can be either 0 or 1, like a light switch that is off or on. Computers process billions of these bits at incredible speeds, but each bit is still just a 0 or a 1 at any given moment. Now scientists are building a completely new kind of computer, called a quantum computer. Instead of bits, it uses quantum bits, or qubits. A qubit does not have to be just 0 or just 1. Thanks to superposition, it can be both at the same time. That sounds like a small change, but the consequences are enormous. One qubit can store both values at once. 2 qubits can store 4 values. 3 qubits can store 8. The numbers grow exponentially. With just a few dozen qubits, you can perform calculations that would take ordinary computers thousands of years. Of course, building quantum computers is incredibly difficult. Qubits are extremely fragile. They are easily disturbed by heat, vibrations, even stray light. When that happens, the superposition collapses, and the qubit falls back into a normal classical state. Still, step by step, scientists are getting closer to building quantum computers that are genuinely useful. Quantum superposition, something that once sounded like science fiction, is becoming real technology. Superposition is strange enough. But the quantum world has something even stranger. Something that made even Einstein, the man who revolutionized physics, shake his head in disbelief. Imagine you have a pair of gloves, one left-handed, one right-handed. You put each glove into a separate box, then send one box to Paris and the other to Tokyo. When you open the box in Paris and see the left glove, you instantly know the box in Tokyo contains the right glove. There is nothing mysterious about this. The information was determined from the start. You simply learned it when you opened the box. Quantum entanglement is completely different. When two particles become entangled, usually because they were created together or interacted closely, they do not decide their states in advance. Like the quantum coin, they exist in superposition. But their states are linked in a very strange way. When you measure the first particle, it chooses a state, for example spin up. Instantly, with no delay and no signal, the second particle, even if it is thousands of kilometers away, also knows. It will choose the opposite state, spin down. Nothing travels between the particles. No radio waves, no signals of any kind. There is not even a time delay. The connection is instantaneous, no matter the distance. Einstein called this spooky action at a distance. He hated it. He believed nothing, not even information, could travel faster than light. That principle sits at the heart of relativity, the theory he himself created. He argued there must be hidden variables, secret information the particles carried from the beginning, like the gloves in the boxes. Quantum theory was incomplete, he said. It was missing something. For decades, entanglement was mostly a philosophical argument. Then, in the 1960s, an Irish physicist named John Bell did something remarkable. He figured out how to test whether Einstein was right. Bell wrote a mathematical inequality, a kind of formula that could distinguish between two possibilities. Either Einstein was right and hidden variables existed, or quantum theory was right and entanglement was real. Scientists ran the experiments. They created entangled particles, measured them, checked the numbers. The experiments were repeated thousands of times, in dozens of laboratories. The result was clear. Quantum theory was right. Entanglement is real. There are no hidden variables. The particles are genuinely connected in a way classical physics cannot explain. Einstein was wrong. There is an important caveat, though. Even though the connection is instantaneous, you cannot use it to send information faster than light. The outcomes of your measurements are random. You cannot control whether your particle chooses spin up or spin down. So even though the particles talk instantly, you cannot encode a message in that conversation. It is like two people at opposite ends of the galaxy flipping coins. Each result is random, but somehow, whenever one gets heads, the other always gets tails. Perfectly synchronized, yet useless for communication. Entanglement is not just a scientific curiosity. It is being used in real technology. Scientists are developing encryption systems that use entangled particles to transmit information with absolute security. If someone tries to eavesdrop, the entanglement is disturbed, and the intrusion is immediately detected. Entanglement is also essential for quantum computers. When many qubits are entangled, they can perform calculations no classical computer could ever manage. There is even a phenomenon called quantum teleportation, not like in science fiction, but the transfer of a quantum state from one place to another using entanglement. It has already been demonstrated in laboratories. The thing Einstein called spooky, the thing he refused to accept, is now becoming the technology of the future. Now let's talk about another strange phenomenon, one that violates almost every intuition we have about the physical world. In the everyday world, if you throw a ball at a wall, it bounces back. If the ball does not have enough energy to break through the wall, it cannot pass. That is just how things work. But in the quantum world, a particle can do the impossible. It can appear on the other side of a barrier it does not have enough energy to cross. Remember the wave function we talked about earlier. A particle's wave function does not stop abruptly at a barrier. Instead, it fades through it, like a whisper through a wall. Most of the wave is reflected, but a tiny part leaks through. That means there is a very small, but not zero, chance the particle will show up on the other side. Physicists call this quantum tunneling. An electron looks at a wall and says, "A wall. I think I'll take a shortcut." It sounds like a fairy tale, but quantum tunneling is real. It has been observed thousands of times and is used in everyday technology. Radioactive decay happens because of tunneling. Particles inside an nucleus are trapped by the strong nuclear force. They do not have enough energy to escape, but thanks to quantum tunneling, sometimes they slip out. That is radioactive decay. Even the sun shines because of tunneling. In the sun's core, protons repel each other due to electric forces. Classically, they do not have enough energy to overcome this repulsion and fuse. But thanks to quantum tunneling, they sometimes do. The result is sunlight warming the Earth. Without quantum tunneling, the sun would not shine. You would not exist. Finally, we arrive at perhaps the strangest idea of all, the quantum vacuum. What do you think empty space is? A place with nothing in it. No particles, no energy, no matter. Just nothing. Once again, the quantum world says, not so fast. Recall Heisenberg's uncertainty principle. It applies not just to position and velocity, but also to energy and time. That means even in the emptiest space imaginable, energy can fluctuate for extremely short moments. These fluctuations create virtual particle pairs, electrons and positrons, photons, quarks, popping out of nothing, existing for a tiny fraction of a second, then vanishing again. The vacuum is not calm. It is boiling with activity. Scientists have even found a way to prove this. There is an experiment called the Casimir effect. You place two ultra-thin metal plates extremely close together in a vacuum. Classical physics says nothing should happen. But in reality, the plates are pulled toward each other by a small but measurable force. Why? Because between the plates, only virtual particles with certain wavelengths can exist. Outside the plates, all wavelengths are allowed. The pressure from the virtual particles outside is greater than inside. The vacuum pushes the plates together. This is real evidence that nothing is not truly nothing. Even when you remove everything from a region of space, something remains: energy fluctuations, virtual particles flickering in and out of existence. So we have come a long way. From superposition, which allows things to be both at once, to entanglement, instant connections across space, to tunneling, slipping through impossible barriers, to a restless vacuum, where nothing turns out to be something. All of these strange phenomena lead to one big question, a question physicists have argued over for nearly a century. When do all these possibilities collapse into a single reality? And who, or what, decides which one becomes real? We have seen electrons exist as clouds of possibility, spread out through space, in many places at once. We have seen the wave function evolve smoothly and quietly according to Schrödinger's equation. Everything seems reasonable, in a strange kind of way. Then you place a measuring device. You look. You check. In an instant, that entire cloud of possibility, the thing that was spread everywhere, suddenly collapses into a single point. The electron is no longer everywhere. It is now here, one specific location, one definite outcome. Before the measurement, it is hazy, shimmering, full of possibilities. After the measurement, it is a point, clear and certain. So what happened in that moment? What caused this almost magical transition from maybe to definitely? How does the universe decide which one of countless possibilities becomes real? This is not a small question. It may be the deepest mystery in all of modern physics. The problem is that no one knows exactly what causes this so-called collapse of the wave function. Is it the measuring device itself? Is it the information being recorded? Does it require consciousness, a human observer? Or would a fly passing by be enough? An atom? A stray photon? Physicists have argued about this for nearly 100 years. They have proposed many answers, many interpretations. And the remarkable thing is that no one agrees. Even today, scientists are deeply divided on this issue. So let's look at three major interpretations, three radically different ways of understanding the same phenomenon. The first interpretation, and the most traditional one, is called the Copenhagen interpretation. The name comes from Copenhagen, Denmark, where the great physicist Niels Bohr worked. Bohr was one of the founders of quantum mechanics, and he spent years thinking about what it really meant. His answer, put simply, was this: stop worrying about what is really happening. According to Bohr, the wave function is not a real thing. It is just a mathematical tool, a convenient way to calculate probabilities. It is more like a map than the actual territory. A map is not the country itself. It is simply a way of representing information about it. In the same way, the wave function does not describe some deeper underlying reality. It only describes what we can say about a system, based on what we know. When we perform a measurement, we gain new information. The wave function, collapsing, simply means we update our knowledge. Bohr went even further. He said that asking, where was the electron before we measured it, is a meaningless question. It is like asking, what color is a trumpet sound, or, what does the number 7 smell like? These questions do not make sense because they apply a concept where it does not belong. In the Copenhagen view, reality does not exist independently of observation. Where only becomes a meaningful concept after a measurement is made. Before that, there is no answer, not because we do not know it, but because the question itself is invalid. This made many people uncomfortable, including Einstein. Einstein famously asked Bohr, so does the moon not exist when no one is looking at it? Bohr replied calmly, physics does not describe the deep nature of reality. It only describes the results of the experiments we perform. This approach has an unofficial slogan: shut up and calculate. Do not waste time on philosophical questions. Use the equations, get the answers, compare them with experiments. Does it work? Yes. Then that is enough. This practical attitude helped physics advance at an incredible pace. It led to atomic bombs, lasers, transistors, computers, all built on quantum mechanics. The equations work beautifully. The Copenhagen interpretation allowed physicists to use the theory without getting stuck in endless philosophical debates. But that does not mean everyone was satisfied. Many scientists still felt something was missing. They wanted to know what was actually happening, not just how to calculate outcomes. In 1957, a young graduate student named Hugh Everett was working on his PhD at Princeton University. He thought deeply about the problem of wave function collapse. Then he had an extremely bold idea, one that many people considered insane. Everett asked, what if the wave function never collapses? Wait, you might say, but we see it collapse every time we measure something. We see one outcome, not many at once. Exactly, Everett replied. You see one outcome, but what if all the other outcomes also happen, just in different, parallel universes? According to Everett's many worlds interpretation, every time a quantum measurement occurs, the universe splits. In one branch, you see outcome A. In another branch, a different version of you sees outcome B. Both outcomes happen. Both are real. They just occur in different universes. Take a simple example. You measure the spin of an electron. It can be spin up or spin down. In the Copenhagen view, the electron is in a superposition until you measure it, and then it chooses 1. In the many worlds view, there is no choice at all. The universe splits in two. In one universe, you see spin up. In the other, another version of you, with the same memories and thoughts as you, sees spin down. Both versions of you are real. Both universes are real. But they no longer interact. Once they branch, they are forever separate. This sounds like science fiction. Parallel universes. Countless versions of yourself. Has Everett been watching too many movies? But listen to the advantages. The many worlds interpretation is mathematically clean. It requires no extra rules. It only needs Schrödinger's equation, the wave function evolving smoothly and continuously, always. No sudden collapse. No exceptions. No miracles. In some sense, it is simpler than Copenhagen. Copenhagen says Schrödinger's equation works most of the time, except when a measurement happens. Many worlds says Schrödinger's equation always works. No exceptions. It also solves a philosophical problem. In Copenhagen, there is true randomness, the electron randomly picks an outcome. In many worlds, there is no randomness at all. Every possibility happens. The universe is completely deterministic. However, this interpretation has some very serious problems. First, it feels wildly excessive. Every quantum measurement creates a new universe. Every second, trillions upon trillions of quantum events occur. That means the universe is branching constantly, endlessly, without limit. The number of universes explodes beyond imagination. Second, it cannot be tested directly. By definition, you can never see the other branches. Once universes split, they never meet again. So how do you know they are real? Is this science, or is it philosophy? Third, what does probability even mean here? When we say an electron has a 50% chance of being spin up, what does that mean if both outcomes always happen? Everett had to redefine probability, not as the chance something happens, but as the fraction of versions of you that will see this outcome. This works mathematically, but it feels deeply strange. Despite these issues, the many worlds interpretation has attracted supporters. Some well-known theoretical physicists favor it. They argue that even if it sounds crazy, it is faithful to the mathematics of quantum mechanics. Perhaps the strangest thing about many worlds is this: if it is true, you will never know. Among all those parallel branches, there are countless versions of you, each convinced they are the original, each living a slightly different life, never aware of the others. Copenhagen says the wave function collapses. Don't ask why. Many worlds says the wave function never collapses, everything happens. But there is a third approach, more subtle, called decoherence. Decoherence is not a complete interpretation of quantum mechanics. It does not answer the question of whether the wave function truly collapses. But it does explain why we do not see strange quantum effects in everyday life. The question is this: why do we not see cats that are both alive and dead? Why is a table not in two places at once? Why does the world around us look so classical, so solid, with no superposition or interference? The answer lies in interaction with the environment. In the laboratory, scientists can isolate an electron, keeping it away from everything else. Then the electron can remain in a superposition, produce interference patterns, and behave according to strange quantum rules. But a large object, like a cat, or a table, or you, cannot be isolated. You constantly interact with your environment. Every second, billions of air molecules collide with you. Light bounces off your skin. Heat radiates from your body. Each interaction carries information about your state. When a quantum system interacts with its environment, it becomes entangled with it. Remember entanglement, when two systems become linked in a quantum way. When a system becomes entangled with trillions upon trillions of particles in the environment, information about its quantum state leaks out. The interference patterns, the signature of superposition, disappear. Not because the wave function truly collapses, but because it becomes entangled with so many other things that we can no longer observe the quantum effects. There is a helpful metaphor here. Imagine walking on a frozen lake. Beneath the ice is water, flowing, fluid, constantly changing, behaving in strange quantum ways. On top is a solid surface, stable, predictable, classical. Decoherence is like the freezing process. It does not make the water disappear. The water is still there underneath. But the ice hides it, creating a hard surface we can walk on. In the same way, decoherence does not remove quantum behavior. It is still there, deep down. But it is hidden by entanglement with the environment, giving rise to the classical world we observe. What matters is how fast this process happens. For a small, well-isolated particle like an electron, decoherence can be slow. We can maintain quantum states for seconds, sometimes even minutes. But for large objects, decoherence is incredibly fast, happening in trillionths of a second. So fast that a cat is never really in a both alive and dead state long enough for us to notice. That is why the everyday world looks normal. Not because quantum rules stop applying, but because decoherence happens far too quickly for us to see quantum effects. Decoherence also explains why quantum computers are so hard to build. You must keep qubits extremely isolated, at temperatures near absolute zero, shielded from vibrations and noise. Because if the environment touches a qubit, decoherence sets in and the quantum state disappears. It is like trying to keep a candle lit in a hurricane. But decoherence does not solve everything. It explains why we do not see interference in large objects, but it does not explain why one specific outcome occurs. When you measure an electron, why do you see spin up instead of spin down? Decoherence cannot answer that. Some people combine decoherence with Copenhagen. The environment causes decoherence, making superpositions vanish in practice, and then some unknown mechanism causes a real collapse. Others combine it with many worlds. Decoherence creates the branches of the universe, making them separate and unable to interact. So we have three perspectives. Copenhagen says reality does not exist before measurement. Don't ask further. Many worlds says all realities exist, across countless parallel universes. Decoherence says quantum reality is still there, but hidden by entanglement with the environment. Three views, three very different philosophies. And the strange thing is that all three make the same mathematical predictions in most situations. All three work in the sense that they give the correct results. So which one is right? The truth is, we do not know. We may never know. It is possible this question lies beyond the reach of experimental science. But there is something even stranger than all three of these ideas. One experiment suggests that reality may not only depend on whether we observe it, but also on what we choose to do in the future. Time, it turns out, may not be as simple as we think. We usually think of time as a one-way road. The past has already happened and cannot be changed. The future has not arrived yet and remains uncertain. The present is the moment where the past turns into the future. Simple, clear, reasonable. But once again, the quantum world is about to shatter our common sense. In 1978, a famous physicist named John Archibald Wheeler proposed a thought experiment that left many people stunned, and even unsettled. He called it the delayed choice experiment. Here is the idea. Let's return to the familiar double-slit experiment. You fire a single photon toward two narrow slits. We already know the rule. If there is no measuring device, the photon behaves like a wave and creates an interference pattern. If there is a detector watching which slit it goes through, the photon behaves like a particle and the interference disappears. Wheeler asked a strange question. What if you decide whether to place the detector or not only after the photon has already passed through the slits? That sounds absurd, right? The photon has already gone through. It must have already decided whether it was a wave or a particle. Your choice now cannot possibly change something that happened in the past. But real experiments showed something very different. Scientists set this up in the lab. They send photons through the two slits, the photons pass through and head toward a screen behind them. In the tiny fraction of time between the photon passing the slits and hitting the screen, they randomly decide whether to turn the detector on or off. The result is startling. If they turn the detector on, meaning they try to see which slit the photon went through, there is no interference pattern. The photon behaves like a particle. If they leave the detector off, the interference pattern appears. The photon behaves like a wave. Even though the decision was made after the photon had already passed through the slits. It is as if the photon somehow knew what you were going to decide in the future and adjusted its past behavior accordingly. As if the photon could look forward in time, see what you were about to do, and choose its path based on information from the future. This sounds insane. It violates our basic idea of causality, the notion that causes must come before effects. How could a future decision influence a past event? And the weirdness does not stop there. There is an even stranger variation of this experiment, known as the quantum eraser. In this version, scientists do the following. They mark the photon in a way that makes it possible to know which slit it passed through. As expected, once the path information exists, the interference pattern disappears. The photon behaves like a particle. Then they do something clever. After the photon has already passed through the slits, after it has already been marked, they erase the path information. They make it impossible to know which slit the photon went through, even when analyzing the data afterward. The result? The interference pattern comes back. Think about that for a moment. The photon passed through the slits, it left a trace, the information existed. But when that information is erased, even after everything has already happened, the interference pattern reappears, as if the photon went back in time and decided to behave like a wave instead of a particle. Some physicists explain this by saying that reality is not fully settled until all information is fixed. Not just the information available at the moment an event occurs, but all information about that event, including decisions made later about whether to keep or erase that information. It is as if time is not a flow from past to future, but a single solid block, a complete picture, where every moment exists at once. What happens at one moment can depend on what happens at another moment, even if that moment is technically later. Before you start thinking about sending messages to the past or rewriting history, there is an important clarification. You cannot do that. Even though delayed choice and quantum eraser experiments reveal a strange connection between past and future, they do not allow causality to be broken in the everyday sense. You cannot send information to the past. You cannot change what already happened. Why not? Because individual measurement outcomes are still random. When you look at a single photon, you see nothing unusual. Only when you collect many photons and analyze them statistically does the interference pattern appear or disappear. Information about the future does not travel backward in a usable way. It only shapes how probabilities are distributed. It is like two people at opposite ends of the universe, each holding a pile of photons. They cannot send messages to each other using those photons, even with quantum entanglement or delayed choice. The laws of physics still protect causality at the macroscopic level. But that does not make the experiments any less strange. They still suggest that the way we think about time, with a fixed past and an open future, may not be how the universe truly works at the quantum level. There is another way to look at these experiments. Information, not matter, may be the true currency of the universe. In the classical world, we think of reality as material objects moving through space over time. A particle is here, then there, then somewhere else. Simple. But in the quantum world, reality does not seem to be locked in until the information about it is complete. Not just information at a single moment, but all information related to the event, across the entire story of the system. An analogy may help. Imagine watching a movie. In real time, you experience it frame by frame, from beginning to end. But physically, the film contains all frames at once. Frame 100 exists at the same time as frame 1 and frame 1000. Quantum time may be similar. All frames, all moments, exist together. What we experience is the act of watching them one by one. But they are not created sequentially. They are a single whole. From this perspective, the delayed choice experiment is not about changing the past. It is about realizing that the past and the future are not as separate as we think. They are different parts of the same whole, connected in ways our everyday intuition cannot grasp. We have traveled a long way through the quantum world. From Planck's tiny packets of energy, to Einstein's photoelectric effect, the strange double-slit experiment, Schrödinger's elegant equation, Heisenberg's uncertainty principle. We have seen superposition, which allows particles to be everywhere at once. Entanglement, instant connections across space. Tunneling, slipping through impossible barriers. A vacuum bubbling with virtual particles. We have debated competing interpretations. Copenhagen, with its mysterious pragmatism. Many worlds, with countless parallel universes. Decoherence, bridging the gap between quantum and classical reality. And finally, we have seen that time itself may not be as simple as it seems. The past may depend on the future. Reality may not be complete until the entire story is told. All of this is real. Not empty philosophy. Not science fiction. These effects have been demonstrated experimentally, measured with precision, repeated thousands of times. The quantum world is strange, counterintuitive, and deeply mysterious. But it is also real. So real that we are now building technology on top of it. Quantum computers, quantum cryptography, quantum sensors, all rely on these very phenomena. Now, let's look at how these strange principles are being applied in the real world, how they are reshaping technology, medicine, and even the way we understand life itself. Before we talk about specific applications, we need to change the way we look at reality once again. Forget everything you think you know about particles. Forget tiny marbles flying through space. In truth, there are no particles, only fields. This is one of the most profound shifts in modern physics, known as quantum field theory. It tells us that everything in the universe, every electron, every photon, every quark, is not a separate object. They are ripples and invisible fields that stretch across all of space. An electron is not a little charged bead. It is a ripple in the electron field, an invisible field that exists everywhere in the universe. A photon is a ripple in the electromagnetic field. A quark is a ripple in the quark field. Imagine the universe as an infinite ocean. Actually, not one ocean, but many oceans layered on top of each other, each with its own waves. What we call particles are simply waves on these oceans. The beauty of this picture is how much it explains. Why can particles be created from energy? Because they are just waves, and you can create waves by stirring water. Why can particles disappear? Because waves can fade away. Why do antiparticles exist? Because waves can oscillate in different ways. Forces, too, are exchanges of virtual ripples, tiny vibrations and fields that exist for such a short time we cannot observe them directly, yet long enough to carry force. You, right now, are not a pile of particles. You are a delicate pattern woven from countless ripples in the electron field, the quark field, the photon field. You are a poem written in quantum vibrations. A melody in the grand symphony of the universe. Now we arrive at perhaps the most striking application of all, the quantum computer. A classical computer is like a careful librarian. It flips through pages one by one, reads each line, and processes information step by step. A quantum computer is like a mad poet. It reads all the books at once, in overlapping whispers, and somehow extracts an answer from the chaos. The secret lies in the quantum bit. A qubit is not just a 0 or a 1. Thanks to quantum superposition, it can be both 0 and 1 at the same time. 2 qubits can represent 4 states at once. 3 qubits can represent 8. The numbers grow exponentially. With 20 qubits, you have over 1 million states. With 300, you have more states than there are atoms in the entire observable universe. That is the power of superposition. Quantum entanglement makes things even more powerful. When qubits become entangled, they form deep connections that classical bits can never have. Like dancers performing a perfectly synchronized routine on opposite ends of the galaxy. But building a quantum computer is extraordinarily hard. Qubits are incredibly fragile. The slightest vibration, a tiny change in temperature, even a stray photon can destroy a quantum state. This is called decoherence, the number one enemy of quantum computing. So what is the solution? Cool the system to near absolute zero, colder than outer space itself. Isolate it from every vibration. Shield it from all electromagnetic noise. Like trying to keep a candle lit in a hurricane. Then there is the problem of error correction. Classical computers can copy data for backup. But in the quantum world, there is a rule called the no-cloning theorem, which says you cannot copy an unknown quantum state. So scientists must invent clever new ways to protect information. Like wrapping a poet in layers of soundproofing so they can keep reciting without being disturbed. Despite these challenges, progress is rapid. Quantum computers could revolutionize many fields. In quantum chemistry, they could simulate molecules with unprecedented detail, helping design new drugs, new materials, more efficient batteries. In optimization, they could solve complex problems like delivery routes or resource allocation that would take classical computers years. In cryptography, they are both a threat and an opportunity. A quantum algorithm called Shor's algorithm could break most of today's encryption systems. But quantum cryptography also promises near-perfect security, grounded in the laws of physics themselves. In 2019, Google announced it had achieved quantum supremacy, when its quantum computer solved a problem that would take classical computers thousands of years. IBM is also developing impressive systems. We are still in our infancy. Today's quantum computers are like the first computers of the 1940s, huge, noisy, error-prone, and expensive. But their potential is limitless. Yet there is something even more fascinating than human-made technology, the possibility that nature has been using quantum mechanics for billions of years. Biology is usually seen as warm, wet, and chaotic. Quantum physics is cold, isolated, and delicate. These two worlds should not work together. And yet, it seems they do. Consider migratory birds. Robins fly thousands of kilometers with astonishing precision. How do they know where to go? One bold hypothesis suggests they have a quantum compass in their eyes. In a protein called cryptochrome, there may be pairs of entangled electrons. When light excites them, they interact with Earth's magnetic field in a quantum way. In effect, birds may be able to see the magnetic field. Preliminary evidence supports this idea. Nature has solved a problem engineers still struggle with, maintaining entanglement in a noisy, warm environment. Or consider photosynthesis, the way plants turn light into chemical energy. Its efficiency approaches 99%, far too high to be mere chance. Recent research suggests that energy inside a leaf may explore multiple paths at once, using quantum coherence to find the shortest route to the reaction center. Like dropping a marble into a maze, but instead of rolling down one path, it spreads out like a wave, senses every path, and then chooses the best one. Even your sense of smell might use quantum mechanics. A controversial hypothesis proposes that the nose does not only detect molecular shape, but also how molecules vibrate. Electrons in large protein molecules may tunnel through odor molecules, with probabilities that depend on vibrational frequency. Your nose could be a tiny quantum spectrometer. The strangest rules of the universe do not stop in the laboratory. They live in feathers, in leaves, in your breath. Life has been quietly using quantum mechanics for billions of years, it just never told us. From strange principles to astonishing technology, from laboratories to living systems, quantum mechanics is not just an abstract theory. It is the foundation of reality, operating right now in every atom of your body. But there is one final question, the deepest one we must ask. What does all of this mean? Einstein once said a famous line, "God does not play dice with the universe." He hated the idea of randomness. He believed the universe had to be a perfect clockwork machine, where everything was predetermined, even if we had not yet figured it all out. But quantum mechanics replies, oh yes, God does play dice. And he seems to enjoy it. When you measure an electron, when you check its spin, the outcome is genuinely random. Not random because we lack information. Not random because our instruments are imperfect. It is randomness built into the very fabric of reality itself. Before the measurement, the electron does not have a definite spin that we simply do not know yet. It truly has not decided. Only when we measure does the universe, metaphorically speaking, roll the dice and choose an outcome. This may sound like chaos. But it is not. It is a very special kind of randomness, structured randomness. Quantum theory does not say anything can happen. It says here is the exact list of what can happen, with the exact probability for each outcome. An electron has a 50% chance of spinning up and a 50% chance of spinning down. Not 49%. Not 51%. Exactly 50%. Even more astonishing, when we calculate these probabilities using quantum theory, they match experiments to 12 decimal places. 12. That level of precision is almost unbelievable. It is like rolling 100 dice. Each die lands randomly. You cannot predict which die will show which number. But the total sum of all 100 dice. You can predict it with remarkable accuracy. Random at the individual level, yet extraordinarily orderly at the collective level. There is something profound here. Randomness is not the enemy of order. It is a different kind of order, statistical order, probabilistic order. More than that, randomness may be the engine of diversity and creativity. Without quantum randomness, there would be no genetic mutations. Without mutations, no evolution. Without evolution, no complex life. No you. No me. Quantum randomness gives the universe choice. It opens new paths, new possibilities. In a fully deterministic universe, everything would unfold like a film already shot. But in a probabilistic universe, there is always room for surprise, for novelty, for something genuinely new. Perhaps Einstein was wrong, not about the math, he understood the math perfectly, but about the philosophy. Perhaps randomness is not a design flaw. Perhaps it is the universe's greatest feature. Randomness changes how we think about prediction and about the future. But quantum mechanics changes something even deeper, how we think about the nature of reality itself. Let us return to the question Einstein once asked Bohr: does the moon exist when no one is looking at it? In the classical world, the answer seems obvious. Yes. Reality is objective. It exists independently of our observation. We are merely explorers, uncovering what is already out there. But the quantum world suggests something different. At the deepest level, reality is not fixed before measurement. An electron is not somewhere that we simply do not know about. It truly does not have a definite position until we look. Observation does not merely reveal information. It participates in creating the outcome. We are not just passive spectators watching the cosmic play. We are actors on the stage, influencing the story by our very presence. This does not mean that positive thinking can reshape reality however we want. You cannot just think, "I want to win the lottery," and have electrons rearrange themselves to make it happen. The influence of observation is subtle, confined to the quantum scale, and governed by precise mathematical rules. Still, the implication is profound. We and the universe are not separate. The observer and the observed are entangled, not just metaphorically, but literally, in the language of quantum physics. You are not merely in the universe. You are part of it. Every atom in your body was once forged in a star. Every breath you take contains atoms that once belonged to countless other living beings. You are the universe experiencing itself. Quantum mechanics teaches us humility. The world is not obligated to be easy to understand. It is not required to fit our intuition. Our intuition evolved to deal with apples and rocks, lions and trees, things of medium size moving at medium speeds. Not electrons and photons. When the microscopic world behaves differently from what we expect, it is not a flaw in the world. It is a limitation of our intuition. So what have we learned from a century of quantum discovery? Not just equations. Not just technology. But deeper lessons, almost spiritual gifts. The first lesson is about uncertainty. Superposition, the Heisenberg principle, randomness, they all point to the same message. Uncertainty is not a defect. It is a feature. In life, we often try to eliminate uncertainty. We want perfect plans, clear schedules, predictable futures. But the universe at its deepest level tells us that absolute certainty is impossible. Rather than seeing this as a problem, perhaps we should see it as liberating. Uncertainty allows novelty. It allows creativity. It allows life to exist. If everything were rigid and predetermined, the universe would be like a stone statue, beautiful perhaps, but frozen, lifeless, incapable of change. The second lesson is about possibility. Before measurement, the electron is everywhere. The photon goes through both slits. Possibility is always present. In the quantum world, nothing is truly impossible. There is only extremely unlikely. An electron can tunnel through a wall. The probability is tiny, but not zero. In theory, all the atoms in your body could simultaneously tunnel through the wall of your room. The probability is unimaginably small, but still not zero. The universe is always more open than we think. There are always more possibilities than what we see at first glance. The third lesson is about connection. Quantum entanglement shows us that two particles at opposite ends of the universe can still speak to each other. Nothing is ever truly isolated. The universe is not a collection of separate, independent objects. It is a web of relationships. Everything influences everything else in ways we are only beginning to understand. The loneliness, the sense of separation we sometimes feel, may be illusions created by our limited senses. At the deepest level, everything is woven together. The fourth lesson is about questions. Richard Feynman, one of the greatest physicists of the 20th century, once said, "No one understands quantum mechanics." He did not say this because he was ignorant. He was a genius. He was simply acknowledging that the quantum world is so strange it exceeds our ability to fully comprehend it. And that is wonderful. Not fully understanding is not a failure. Sometimes the question is as beautiful as the answer. Sometimes mystery is what keeps us exploring, curious, and filled with awe. A world we fully understand would be a boring world. But a world full of mystery, full of unanswered questions. That is a world worth living in. The final lesson is humility. We often think we understand reality. We have clear ideas about space, time, matter, cause, and effect. Quantum mechanics gently whispers, "Not yet. You have only just begun." Our knowledge has limits. Those limits are not because we are foolish or lack tools. They are built into the structure of reality itself. The Heisenberg uncertainty principle is one example. There are things we cannot know, not because we are not good enough, but because the universe does not allow it. And that is a gift. It means there will always be more to discover. No matter how much we learn, no matter how advanced our technology becomes, there will always be mysteries, wonders, things that leave us astonished. So what do all these ideas, superposition, entanglement, randomness, uncertainty, mean for your everyday life? Practically speaking, maybe not much. You still have to go to work, cook dinner, take care of your family. Quantum mechanics will not help you find a parking spot or decide what to eat tonight. But philosophically, in how you see the world, it can change everything. It reminds you that reality is deeper, richer, and more wondrous than what your eyes reveal. The table in front of you is not the solid object it appears to be. It is a dance of countless quantum fields, vibrating ripples, particles flickering in and out of existence. It reminds you that you are connected to the universe in ways you cannot see. Every photon of sunlight that touches your skin has traveled 8 minutes from a nuclear furnace 150 million kilometers away. Every breath you exhale contains atoms that may once have been part of a dinosaur, of Julius Caesar, of a distant star. It reminds you that uncertainty is not the enemy. Your life is not carved in stone. The future is not fixed. There is always room for change, for choice, for new possibilities. These lessons may not change what you do each day. But they can change how you feel about living, about being part of this strange, beautiful universe. We have come a long way together. From strange questions about quantum coins, through discoveries that reshaped the world, to deep reflections on the meaning of existence. Now it is time to pause, breathe, and reflect on what we have learned. The quantum world is strange. But it is also real. More real than what our eyes see. More real than what our intuition tells us. It is the foundation of everything, vibrating right now in every atom of your body. You are quantum. You are wave and particle. You are possibility and reality. You are part of a universe discovering itself, a cloud of probabilities that observes, wonders, and exists. That is the final gift of quantum mechanics, a way of seeing the world as more mysterious, deeper, and more beautiful than we ever imagined. Thank you. Thank you for giving your precious time to this small journey. Thank you for letting your ears listen, your mind think, your heart feel. Thank you for trusting the strange, for being willing to sit with the unknown, with what cannot be fully understood. If you have fallen asleep, that is wonderful. The quantum world will still be here when you wake up. It is not going anywhere. In fact, it is everywhere, in every atom around you, in every ray of light that will touch your eyelids when you open your eyes tomorrow morning. If you enjoyed this journey, please like, subscribe, and share the sense of wonder with the people you love. This small channel needs your breath, those tiny interactions, to keep flying, to keep carrying stories about the universe to more minds. Sleep with knowledge, where science meets dreams, where reality meets poetry, we leave you with these final lines. In the smallest world, certainty breaks. And in that breaking, beauty is born. Reality is not rigid, but gentle. Not hard, but shimmering and poetic. Perhaps, just perhaps. That is why it is so wonderful. Good night. Sweet dreams. Dreams of other worlds, other possibilities, other versions of yourself across countless parallel universes, if the many worlds interpretation is right. Remember this, even as you sleep, even as your consciousness drifts into distant lands, the quantum fields are still vibrating around you. They whisper the rules of existence. They weave reality moment by moment. You are never truly alone. You are held in the arms of the universe, surrounded by invisible fields, connected to everything else in ways science is only beginning to understand. That is the final gift of quantum physics, a reminder that you belong here. You are an inseparable part of this astonishing universe. You are ripples in the quantum ocean. You are a poem written in vibrations. You are the moment when the universe opens its eyes and sees itself. Sleep well, our friend. The quantum world, strange, beautiful, and forever beyond full understanding, will still be here. Always. Forever. In every grain of dust, in every beam of light, in every breath. And that is the most beautiful thing of all.